So here's a quick disclaimer, I guess, for the video that I'm about to, that follows. When we're working with dielectrics, lots of times you'll see, this 1 over 4 pi epsilon naught turn into this 1 over 4 pi epsilon, where this is the permittivity of the dielectric. In the following video, I sometimes refer to this as the dielectric constant. And I think that's fairly widespread for people to kind of use those terms interchangeably. But Griffiths kind of makes this more clear. If you look at equations around like 4.33, 4.34 in Griffiths' book, the fourth edition, he kind of nails this down very specifically, saying that the permittivity of a material for a linear dielectric is equal to, he uses epsilon, he uses the other kind of epsilon that looks like this, but anyway, is equal to this epsilon sub r times the epsilon of the, meaning the permittivity of free space. And this here is actually the dielectric constant, which for a linear dielectric is 1 plus the susceptibility, or the electric susceptibility of the material. So I guess I just wanted to be clear, even though I use the term dielectric constant for this epsilon instead of saying permittivity in this video, if I want to follow Griffiths more exactly rather than being all kind of loose about it, as I think, at least in what I've read, people are fairly loose with it. What I should have said is this is the permittivity of the material, because the dielectric constant would actually be a dimensionless number that just gives us the ratio of the permittivity of the material to the permittivity of free space. So lots of epsilons running around. I think that's why people are a little bit loose with the terminology. All right, so this time we are looking at a dielectric sphere, so an insulating sphere placed in a uniform external electric field, and we are going to try and find the induced dipole moment of this sphere, and then we're going to try and find, if we put this in, if we assume it has sort of the same dipole moment, and we put it in the field of a point charge, kind of what happens there? Is it pulled towards the charge or away from it? So this is basically like the case of the conducting sphere and the uniform electric field, except now we don't get the full charges moving all to the right and to the left. Instead we get this induced polarization of the material. So, and then based on the dielectric constant, it will tell us how much this will actually polarize. So we have this this dielectric constant of epsilon here, which we'll compare to the permittivity of free space. Basically, if this epsilon, the dielectric constant, goes to infinity, then these charges in the dipoles can move infinitely far away from each other, and basically you should recover the case of the conducting sphere as we move this to infinity. And as we move this to the other end, where this matches the outside epsilon naught, then basically the whole term for this sphere should go away, and we should just be left with the external electric field. So that's kind of first what we're going to do, is solve for the potential inside and outside, and then we'll get to the dipole moment. So just in general, the potential is going to be a sum from n equals 0 to infinity of a sub n times r to the n plus b sub n divided by r to the n plus 1. I'm going to go ahead and make this a see over here, and our Legendre polynomial of cosine of theta. Okay, any azimuthally symmetric problem can be, or potential can be written like this, and we have azimuthal symmetry because if you were to rotate this around an axis through the sphere this way, we wouldn't see any difference at all. So we'll go ahead and look at this. I'm going to try to use this purple color here for the inside and green for the outside, but we'll see if this actually works out. So, what can we say right off the bat? Well, we know that for the outside, just like in the case of the conducting sphere in a constant electric field, at very large R, this is going to be equal to minus E naught. This is the big E naught. This is the strength of the external electric field, multiplied by R cosine of theta. Okay, and what theta is I don't know if I want to draw it here, but it's basically the angle with respect to this external field, right? So generally we'll take our coordinate system to be the center of the sphere with this angle here as theta. Alright, so very, very far away. Basically r cosine theta, right, that's just z, and we have a minus e times z is equal to r potential. Right. So you take your gradient right along there, you just get a nice, constant electric field. You take the minus the gradient of potential on the outside. So on the inside, and also, so what will this tell us? This will tell us, we'll match up A1 in a moment, but all of these other r to the n power here, these are all going to blow up way outside. So we're only going to keep one term. It will turn out, when we look at the Legendre polynomials, it'll turn out to only be the a sub 1 term. All the other ones are going to be 0, so I'm going to write that out here. A sub n, this is for the outside, equals 0 for n not equal to 1. And that's what I get for using a cheap marker. Alright. Switching to this other green. Let's see how this works. Wow, I just broke right off there. Okay. Well, whatever. Moving on. We have okay, so that, alright. Okay. Good. Okay. So now let's look at the inside. For the inside, what we can say is we don't want it to blow up because of these r's here on the bottom here. So I'm gonna, for the inside, let's use an m instead of an n. B sub n will equal 0 for all. sub m. Okay. All right, so we have some other boundary conditions we can use. One of them is that if we, let's just use this one. So V out, that R equals, I'm going to use big R for the radius of the sphere. Okay. We'll just draw that in here, big R. Okay. V sub out is going to be equal to V sub in at the radius of the sphere. Okay, and also, or another way you could do this is at the parallel component of the electric field is going to be continuous. These will basically give you the same restriction on your coefficients. The other one we're going to use is basically that the perpendicular component of the displacement field is going to be continuous. Okay, and basically what that means is once you deal with the minus sign and everything, so on the outside you'll have something like this, and this is just the radial component, right? Because we're taking the perpendicular component to the surface of the sphere, which is just the radial. Okay. And on the inside we have this dielectric constant. Okay, so these are basically our two conditions, or equivalently, you can use either of these two to get the same restrictions on your coefficients. So let's go ahead and do this. So all right, so we're going to start with this boundary condition up here, right? Or you can use this one, you get the same thing, but so we'll start here with the inside. Right, so for the inside we had all the B parts going to 0, okay? So all that was left over was a sum over these parts here, okay? So on the inside, and I was just using the index M for the inside. All these B's go to 0. We have A sub M, R to the M, and then the mth Legendre polynomial, like this, okay? And then for the outside, we had all of the A parts in this sum, the A sub n's, they're all going to go to 0 except for A sub 1. That's going to go to minus big E naught, the strength of the external electric field. So I'm going to write that term out here. In front, so we don't get it confused with the rest of the sum, okay? So this added to a sum over n equals 0 this is a b sub n over r to the n plus 1 Legendre polynomial. Yeah. Okay. All right. So basically, these two sides are going to equate term by term because we have an orthogonality relationship with these Legendre polynomials. So that means let's just write out a few of these Legendre polynomials. Okay. Okay. I think I only know the first three really, and even then it's tricky for me. So when n equals 0, and this is all of only the cosine. Okay, so you can replace this cosine of theta by whatever. That's just going to be equal to 1. The first, so that's the 0th one. Here's the first one is just going to be equal to cosine of theta, and the second one is going to be equal to 1/2 3 cosine squared of theta minus 1. Okay, and then there's higher orders, higher and higher. But because of the orthogonality of these, all of the terms with this one, you can have an infinite number of equations where you bring all of the p sub 1 terms into one equation, and all of the p sub 2 terms into its own equation, and all of these things like this, right? So we're going to, since we have this term right here, right, this depends on cosine, right? So that's this guy right here, just 1 power of cosine, and not mixed in with higher powers of cosine. This is related to, it's a term of the p sub 1 part. So we're going to have two different equations. One is just for the p sub 1s and all of their coefficients and friends, and then one will be for all of the other Legendre polynomials. All right, so we'll start on a new sheet here. So this is for the p sub 1 cosine theta terms. So our m is equal to 1 on this side, p sub 1, and the n on the other side is equal to 1. Like that. Okay? All right. So here we go. This is the p sub 1 terms. So for this left-hand side here, we are going to get an a1. So m is equal to 1. a1 times r times cosine of theta. And on the right-hand side, what do we get? We get this term up here minus e naught r cosine of theta plus a b1 over r squared cosine of theta. All right, so I just used an n equals 1 here, so r squared would be 1. All right, so this is our equation for these first order Legendre polynomials. All right, p sub n greater than 1. Okay. And all right, I'm going to draw just a line between these two so we keep these two cases separate. And again, the reason we're separating this out is just because of this electric field here. Okay, and that gives us this term. So we're just putting, since this term involves the cosine, we're putting it with its buddies, keeping everybody else separate. All right, m is equal to any m greater than 1, and n is equal to any n greater than 1. Okay. All right, so what do we get for this? Well, we get an a to the m, r to the m, Legendre polynomial of m, cosine theta, or an mth order Legendre polynomial. And that is going to be equal to this other side. And I took away the sum, right, because we're looking term by term. So rather than an infinite sum on this side and an infinite sum on this side, we're looking at an infinite sum of equations. They're equated term by term. So here we have a b sub n over, and I'm going to go ahead and switch to an m on this side. And why can we do that? Because these Legendre polynomials are going to be equal on each side, right? So that's why we can do that. The Legendre polynomials are going to force p sub m to be equal to p sub n, right? So m is equal to n. All right, so here we go. And I'm going to go ahead, well, yeah, we'll just write it on the bottom. So p sub m cosine of theta, and then on the bottom here we had an r to the m plus 1. Okay, so here's our two equations. And again, we're just still working with the first boundary condition. So let's see what we can do with these guys. We can divide immediately by cosine of theta. And what else can we do? We can bring this guy over. So I'm just going to write this in black. Black is the new black. Alright, so what I'm doing, after we divide by cosine, all we have is this, I'm going to add this big E naught times r to both sides, alright? And then I'm going to factor out the r. Okay, and all we had left on this side was b1 over r squared. I'm going to multiply both sides by r squared. So now we have an r cubed on this side. Okay, and there's one important thing I've forgotten here, and that is because we are working at this boundary condition, these equations are only valid at the boundary. Okay, I'm not sure where I messed up with this exactly, but remember this, little r equals big R, little r equals big R. So this is a big R. Okay, and I can write that for these guys too, just to be not complete. Yeah, so really I can put a big R, you know, right here, and right here, right here, right here, right there, okay? Alright, so here's our first equation. This is our n equals 1, or m equals 1 equation. Alright, what's our other? Well, now we go and we work with these guys here. So, let's see what we can do with this. Well, the Legendre polynomial is going to be the same for each of these equations. So that can divide out. And then we're just going to bring this r up to this side. So we will have an am, big R, and there's one power to the power of m, and then we're going to multiply it by r to the power of m plus 1. So we end up with an r to the 2m plus 1. Okay? And then all that's left on the other side is a b sub m. All right? So these are coming from our, which one was out again? Out was the green. So b out at evaluated at r equals r is equal to b in evaluated at r equals r. Okay, that's these equations came from that boundary condition. All right, so now let's go ahead and we're going to move to our next boundary condition, which was, okay, so I'm going to set this paper aside, and when we find our new restrictions on our coefficients, we're going to put them also on that paper and collect them all nice in one spot. So now let's look at this boundary condition, okay? I'm going to start on the right-hand side and just flip this over. Okay, let's just do this. So on this side we have our dielectric constant, so we're looking at this side again, all right? And I'm going to write this derivative out here and put in our equation for the v in part, right? So all that was happening in this one where all the b's go to 0. All right, and I'm going to go ahead and just use m for both, since we decided m and n were going to be equal due to the orthogonality of these Legendre polynomials. So what I want is an a sub m to the multiplied by r to the m multiplied by the m. Legendre polynomial, okay? All right. And that is going to be equal to the same thing except for the outside. So now we have permittivity of free space since it's a vacuum out there. Oh, and I have to be careful and say that this is evaluated at little r equals big R. I won't put that in until we take this derivative, though. Okay, so now we are going to do the same thing for the outside. All right, so for the outside, we had our lonely a term, right, minus big E naught r cosine of theta, and you know what? I should have written a big sum here, but what we can do again is just go term by term. And so this term is only there when this is a really awkward way to write this, so sorry about that. Only when m equals 1, okay? Otherwise this term is not there. Ugh, really awkward. Okay, but again, what I'm doing is just like we did before, where we break down the we broke this one down, right? When m and n are equal to 1, we had one equation, and when they're not equal to 1, we had a separate equation. Again, all because of this term here for this constant electric field out there. All right, so I hope this is clear enough, right? Basically, when we're doing it into two equations, but rather than write two complete separate equations, I'm going to put this term in parentheses because that's the only part that's different. All right, so one equation is with this in here, and all the other equations are without this in here. And so we're just going to write it in general. Oh, this is so, I hope it's not too confusing, but so our outside, we have these b sub n, right? R to the n plus 1, and then multiplied by p sub n, and then this cosine of theta. Hard to read, but we all know what it is, right? Here's our parentheses, and this is also evaluated at little r equals big R. Okay? So, again, sorry for writing it that way. Let's go ahead and split these up now. All right, so for m equals 1, we'll have one set, and for m greater than 1, we'll have another set of equations. I guess m equals 1 is not a set, it's just one equation. All right, so for m equals 1, we have epsilon. So we're looking at this term now with m equal to 1. It's a confusing problem all by itself, but when you throw in a bunch of weirdness as far as how I write it, that makes it even worse. Okay. So yeah, like I say, we're going to go ahead and write this out so it's more clear. Okay, so here I just need this. Like that, all right? And then out here on the outside, it's just going to be the same thing, except now we're just going to leave the m in there since this stands for all of the equations. M can be anything larger than 1, an integer, by the way. Of course. Alright, so I hope this makes things a little bit better. Good thing you can fast forward when you watch this stuff on YouTube, right? Okay, so again, this term was only in there when m equals 1. Now it's gone, and we have our b sub n over r to the m plus 1, and then always run out of space for this poor Legendre polynomial here at the end. Okay? All right. Whew. Okay. Got that off of our chest a little bit, so we wrote it a little bit better. All right, let's go ahead and evaluate this. All right, so this top one, we're just going to take this derivative with respect to r. So here we have an epsilon, and then all that's going to be left is a1. The r goes away because of the derivative, cosine of theta. And it's evaluated at r equals r, but it doesn't really matter that much because there's no r left. All right, here we have an epsilon naught when we take the derivative here, we are going to end up with a minus E naught cosine, yes, still got cosine in there, and a minus 2 B1, I'll write that down here, minus 2 B1, now it's an R to the third power on the bottom, cosine of theta. All right, and our cosines can all divide out, so that's great. And again, this R here, this is all evaluated at little r equals big R. All right, so let's just go ahead and get this one over here. So we have an epsilon times A1 from this side. Now I'm going to go ahead and bring this one over, so we get a plus epsilon naught, and soon I'll have to abandon the different colors because this is just going to get crazy. And over on this side we have a minus 2B1, and I'm going to write the big R3. Okay, oh, and there's this epsilon naught over here too. Alright, let's just go ahead and write that on our nice little equation sheet. Okay. How should we do this? We'll just write it the way it is. Okay, so we're going to come back later and work out these equations, obviously. Okay, so that's our m equals 1 equation, just like we had up here, the m equals 1 equation. Now let's go back and look at the for m equals everything but 1. Again, these are all positive integers, so alright, so we're looking at this. Okay, so one thing we can notice is that we're taking these derivatives, right? These Legendre polynomials do not depend on R. So basically, with respect to R, they're a constant. Bring them outside of the derivative. And since it's the same on each side, they're all going to cancel out. Okay, so this is going to cancel with this. Okay, right? And what else? That's about all we can say for that. So now let's go ahead and do our derivative. For the left-hand side, we have our epsilon naught right here, and then we're going to take the derivative of this. So we have an m multiplied from this. I'll write the constant a m out here. R to the m minus 1. Alright, so here's that derivative part, because we just have an r to the m on this side. And on the other side, what do we have? I'll write our bm here out front, and epsilon naught. Now we're taking, well, I'll just write this out. The derivative with respect to r of, I'm going to bring this up to the top, minus m minus 1. Okay, so I just think this makes it more clear when we talk about the derivative. Here's our epsilon naught, and now we have our minus m minus 1 term coming down, and an r to the minus m minus 2. Okay, so here's our other equation that we're going to put on our sheet, but we need to, let's see if we can simplify this at all. I don't know. Yeah, we Well, basically, probably the best thing to do is just to bring this minus sign out and then deal with this r part. So I'm going to write a and epsilon. We had an m here, and then I'm going to multiply both sides by m plus 2. Is that correct? I think so, right? Because we bring this down here, it's an m plus 2, r to the m plus 2. So I'm going to multiply both sides by m plus 2. So that gives us here an r to the 2m plus 1 on this side. And then once so this is after multiplying both sides by r to the m plus 2. We were going to bring out this minus sign. Okay, so this part goes away. So now we're just dealing with what we have here. Bring out the minus sign if we have an m plus 1 in there. Epsilon naught, of course, and a b to the m. All right, if I haven't made any mistakes so far, it's really going to bite me, and I'll have to go back and find it. But so our other equation here is a to the m. All right, bring this epsilon out so it matches this a little bit. Then we multiply by m, r, and again, this is evaluated at little r equals big R, so I'm going to put the big R in there. 2m plus 1 equals minus m plus 1 epsilon naught bm. All right, so all of this came from the epsilon naught dv out by dr equal to epsilon dv in by dr. All right, so here's a good checkpoint. Again, way down the road, we're looking at the eventually we'll look at the dipole moment of this and its energy in the field of the point charge or whatever. But here for the moment, what we've done is we've used our boundary conditions, meaning the perpendicular component of the displacement field. We probably got rid of a minus sign if you want to actually write the displacement field out, right? Okay, and here we just, the potential has to be continuous, right? So we use this boundary condition and this boundary condition, and we got these 4 equations, all right? So so way back in the beginning we had our general potential, and we had these constants, and the thing of it is that because of our uniform electric field out there, we had one term out at infinity for the a sub 1, right? And that made us have to write a separate equation just for the case of the a sub 1 and b sub 1, right? So we had to write these separate 2 equations. All right, so those are our special cases. Otherwise, we just have 2 equations, 2 unknowns. So looking at these, what do we have? Well, right off the bat, what we're going to do is we can say, let's just solve for this bottom case first real quick, okay? So I'm just going to switch to black now. So what we have, this a sub m r to the 2m plus 1 equals b sub m. Look right here. Here's an a sub m, and here's an r to the 2m plus 1. So that means I can write this epsilon, this m, and then I can just write a b sub m. from here, I'm plugging that into here instead of this stuff. Okay, so we have a b sub m on each side, and the thing of it is unless this m plus 1 multiplied by epsilon naught equals minus epsilon m over here, which in general it doesn't, then b sub m has to equal 0. Okay, that's the only way for this equation to hold true, unless you had some crazy specific constraint on a very, very special epsilon here or something, which we don't, right? Okay, and hey, if b sub m is equal to 0, a sub m is equal to, you know, just this constant here multiplied by that. That means a sub m is 0 too. Again, these are only for m greater than 1. Okay, 2, 3, 4, 5, 6, 7, all the way up to infinity. All right, well that's great, because now all of that goes away, and we are just left with 2 equations, 2 unknowns. Highlight this in some different color. How about a nice red? All right. So this equation, looks more orange to me, and this equation right here. Okay. This is what we're left with. All right. So, hey, why not? Let's plug in for b sub 1 first. Let's plug this in for this b sub 1, since it's already kind of set up for us. So I'm going to write a line here, and we have a1 plus big E naught multiplied by r cubed. All right. So that is, whatever, I'll copy it over here. B sub 1. All right. So that's, whatever, I wrote it twice. So here we go. We're taking this and we're going to plug it into this one. Wrote the wrong equation. Okay. Epsilon a1 plus epsilon naught e naught, like this, equals minus 2. I'm just going to bring all the other parts here out front, and now we're going to plug in this b sub 1, right? This is just equal to this. a1 plus e naught times r cubed. Okay? Well, looky here, this r cubed goes away. That's nice. Alright. So what we are left with, let's just multiply everything out and bring it all back together. Is this. Okay, I'm almost out of memory, so let's see if we get through this. Okay, so epsilon plus 2 epsilon naught. So I'm bringing this term over here, mixing it with this a1. Okay, now let's bring this guy over here. Minus 3 epsilon naught big E naught. Okay. All right. So a1 is equal to minus 3 epsilon naught big E naught over epsilon plus 2 epsilon naught. All right. So we just solved for one of our coefficients. So that's great. We have one more to solve for. And now that we solve for this, we can just plug it right in. So where did it go? Here we go. So So we need to go and plug that into this equation here. All right, so here we have an epsilon. Now we're going to plug in this guy right here. Minus 3 epsilon naught E naught over epsilon plus 2 epsilon naught. Alright, so all I did was put in this A1 into this slot right here, okay? Plus epsilon naught, so now I'm on to this term, E naught equals minus 2 epsilon naught over R cubed, and then this B1, okay? Because that's what we're solving for now, is this B1. So let's see if we can simplify this at all. I'm going to put, well, all right, first of all, let's just take out this epsilon naught guy, because he appears all 3 places. All right, or epsilon minus 3 epsilon plus 2 epsilon naught. Okay, here's this part. Let's go ahead and put well, we can just do a plus 1 here, can't we? And factor out this epsilon, or this big E naught. Okay? And then we're going to multiply both sides by an R cubed and divide by 2. And there is a minus sign. Well, I'll just keep that for now. Minus B1, okay? All right, can we make this pretty at all? Let's see. I can combine this into here. So like a minus 3 epsilon plus an epsilon plus 2 epsilon naught for this one, all divided by epsilon plus 2 epsilon naught. Okay, and go ahead and put that minus sign over from here. Oops. Okay, so now we don't have this minus sign, okay, because I put it in here. All right, yeah, we're almost there. We can go ahead and write this out. So all we have here is we can factor out a 2 as well, because when we basically this is just, we're going to subtract. Let me just write this out a little bit. So a 2 epsilon minus 2 epsilon naught. Okay, that's what this top part becomes, right? 3 minus 1 here, and then we have this minus sign on this guy. So I'm going to factor out a 2 and divide it by 2 with this, okay? So all we have left over is big E naught R cubed, okay? The 2 goes away, and this 2 goes away, and we have here epsilon minus epsilon naught divided by epsilon plus 2 epsilon naught. Okay, all right, again, if I made a mistake on this, it's going to give me a headache to go back and find it, but here we go. We have solved for B1, we have solved for A1, and now it is time to gather everything back together and see what we get. So, our potential, the moment we've all been waiting for, right? I don't know if I can go back and find it, but basically all the B's were going away for the inside, right? Whatever, we'll just, so all of our other terms went away except for the n equals 1 term. Okay, so that was the b's all went to 0. Right, so we don't have that there. We have an a1 times r times cosine of theta. Okay? And outside, we had our minus e naught r cosine of theta plus a b1 over r squared cosine of theta. Okay? Is that right? I think that's right. Right? All the other higher terms went away. So, let's write this out real quick. All we have to do is plug in a1. Here's a1 minus 3 epsilon naught big E naught over epsilon plus 2 epsilon naught times r times cosine of theta. Okay? So there's our 1 there. Great. Now, here we go. I'm going to write out the outside. We still have our ever-present term for this that we get from that field way out there. And then we have this guy. I'll bring this dude out front. So epsilon minus epsilon naught over epsilon plus 2 epsilon naught. Okay? Then we have our big E naught. We have our big R cubed here on the top, and our big R, our little r squared on the bottom, and then we have our cosine B. All right, so we can basically, now we have solved for the potential, so let's clean this slate a little bit. We can get rid of all of this. Sorry for the noise. If I can find it, I'm going to keep our first page here, right? Because this had our nice picture that showed us what we're actually doing here. All right, so let's take a look at this in terms of our dipole moment. Okay, the potential for a dipole, we'll have a 1 over 4 pi epsilon naught, and then we'll get a PR cosine of theta over r cubed, right? Or you can write this as like 1 over 4 pi epsilon naught p dotted into r hat, if I wrote that right. Okay, p dotted into r hat over r squared. Oh, this is what I meant to say was an r hat right here, okay? So this extra r on top and r on the bottom, that's how we got this r hat thing. Okay, I think I wrote that right. Okay, so now we are looking at the outside here, okay? And so here's our potential here on the outside. And I'm going to go ahead and write this slightly different. Actually the same, right? I'm just going to divide out this r, right? And I'm going to bring this cosine over r squared out here. Okay, so by comparing this outside potential to the potential of a dipole, look at this cosine of theta over r squared. Well, here also is a cosine of theta over r squared. Okay, and so, oh, and then by the way, this potential, right? This is the part from the field, right? Take away the whole sphere, and here's what you get. By the way, before we do this real quick, we mentioned like what happens in the case of the conductor. So in the case of the conductor, right, we're going to bring epsilon up to infinity, and basically it's on the bottom, right? So this whole thing goes to 0. We have the whole inside is equal to 0, just like we found for the conducting case. And this in the limit as epsilon goes to infinity, this will turn to 1. Okay, so this right here should be what we found for the conducting case as well. All right, and in the case of, yeah, so in the case where the dielectric constant, basically where it goes to the vacuum, the permittivity of the vacuum, basically the sphere is not here is what we should get, right? So if this goes to, if epsilon here goes to epsilon naught, then we have a 3 epsilon naught on the bottom, a 3 epsilon naught on the top, and we just end up with a minus big E naught r cosine of theta. And that's just our term for the constant electric field, right? So that just tells us the sphere is not even there. The field is just goes on right through this space, no change whatsoever. And that says this epsilon goes to epsilon naught. And down for this case, we have this up here, epsilon goes to epsilon naught, this top part will go to 0, and this whole thing goes away. And again, we're just left with the potential, the constant potential that we started with. Okay, so just a note about that before we move on. Right, so here's our term for the constant potential that we had, and here's our term for the sphere. So we're comparing this to the dipole to get the dipole moment of this sphere. So again, we have the cosine of theta over r squared, cosine of theta over r squared, and that tells us that 1 over 4 pi epsilon naught times p is equal to, and this is a little case p, I don't know if that's clear, is equal to epsilon minus epsilon naught over epsilon plus 2 epsilon naught, right, from here. And then the only other part we had was this E naught and R cubed. Okay? This tells us that the dipole moment, I put a vector because we'll show its direction in a second. So we have I'm just going to leave it as a 4 pi epsilon naught. I don't want to mesh this epsilon naught in with everything else. Big E naught R cubed. All right, so again, we put a vector symbol on this. So what direction is it pointing in? Well, the dipole goes from minus to plus, right? Here we have, just like, anyway, the charges on the inside here, like if we were to follow this line across, we have a minus, plus, minus, plus, minus, plus. All right, these two are going to kind of cancel out. Those two are going to kind of cancel out. Anyway, we end up with a plus charge, right? The positive charges want to go in the direction of the field, so we end up with a slight plus charge on this side and minus charge on this side. So the dipole moment is in the same direction as the electric field, right? Or the z direction, right? We could just put a z hat on the end and call it a vector, right? So here is our dipole moment for this sphere, right? 4 pi epsilon naught times this epsilon minus epsilon naught over epsilon plus 2 epsilon naught times the external field vector times the radius of the sphere cubed. Okay, so now that we have our expression for the induced dipole moment for a dielectric sphere in a uniform electric field, E naught right here, we're going to look at the case of where we take this dielectric sphere and we bring it into the presence of a point charge. So the point charge has its own electric field, right? And we're going to try and find the force that's on this dielectric sphere. And we're going to make the assumption that we're far enough away that the field is fairly uniform out here, and so the dipole moment that we found can be a good approximation for the dipole moment actually put on the sphere. So first, in order to find P, we need to know what this E is, this E naught, right? So I'll just call that E naught. Why not? Keep the same notation. That's due to this point charge. So we have a 1 over 4 pi epsilon naught. We have a big Q, and then it goes as r squared, where r is the distance from this point charge, and that's in the radial direction. All right, so when we plug that into here, we get our induced dipole moment. All right, so basically we're taking this and putting it right into here. Now this 4 pi epsilon naught on the bottom, that's going to divide out, so we don't even have to worry about that. So I'm going to start right here. So we have an epsilon minus epsilon naught over an epsilon plus 2 epsilon naught, like this, okay? All right, E here is what we're plugging in. So we have a Q, and then we have an r cubed from up here, and then we have our r squared, and it's in the r hat direction, right? So that makes sense, right? And if we zoom in on our little dipole, there will be a slightly negative and positive like this, and this is the r hat direction. You know, if it were up here, the positive would be right here, and the minus would be right there, which again is in the r hat direction. All right, so no matter, we're covered. We're still describing the general case. Okay, so now we're going to look at the potential energy, and then we'll find the negative gradient of this to get the force on this dielectric sphere. So we have our dipole moment dotted with the electric field that it's in. So, and we have this minus sign as well. Well, we still have this piece right here, and we have this piece right here. So let's just go ahead and do this. They're both in the r hat direction. We don't have to really, this dot product is just a normal product. So they're all in the same direction. So here we go. So this minus sign right here. Okay, now I'm gonna bring down this 4 pi epsilon naught. It comes back into our lives. I'm gonna go ahead and write this now. E minus epsilon naught over E plus 2 epsilon naught. Okay, now we're dealing with these right here. So we have a Q squared. We have this r to the cubed, or to the third power, r cubed. And then on the bottom we have r to the fourth power. Okay, so this is the potential energy of our dielectric sphere in the electric field of this point charge. Now I'm going to try and do this on one sheet. So we've got Now we want to find the force on this dielectric sphere, which is going to be the negative of the gradient of this potential, which we just found. So that's just right down here. All right. It only depends on r, so we only have one derivative to compute. I'll put a little subscript r right here just so we know we're moving into the, since we're looking at this case where it only depends on r, okay, something like that. All right, so yeah, so we just have to take the derivative with respect to r, and we got an extra minus sign here. So our force, yes, and this is in the r hat direction, right? Okay, so again, this is the only component, so away we go. We have r, I'm going to bring this up here, r to the minus 4 up here, okay? It's just easier to think of it when we take the derivative. So we're going to have a minus 4 over here, and that's going to cancel with this 4 and with this minus sign, but we have this other minus sign from way up here when we find the force. So there's still going to be a minus sign, but this 4 is going to cancel with that 4. Okay. So I'll just write 1 over 4 pi. Oh, I mean pi over pi epsilon naught. The 4 is the part that went away. Okay, now we have our good old term with all the epsilons in it, like this. Okay. Anything else? I think we're good. We just have to, I think I can squeeze it in. We'll live dangerously here. So we have a q squared, an r to the third, and a little r to the fifth downstairs. And yes, so this is in the r hat direction. Barely get it in there, okay? All right, so here is the force on this dielectric sphere in the presence of this point charge. Assuming that, this is a first order type estimation based on, we're assuming the field is approximately uniform out here where this sphere is located. All right, you can see this force drops off as r to the 5th power, so really, really quickly. But this sort of force is kind of what's responsible, like when you rub a balloon on your hair and you stick it to the wall, or you use it to pull, if you put it next to a faucet with a thin stream of water, and the water will bend towards the balloon or the comb or whatever you have charged. You're inducing dipoles in the wall, or taking advantage of the dipoles in the water, right? And there's an attractive force between the wall and the balloon. All right, this is obviously a much more simple example where you just have one point charge and a perfect sphere, right? So it gets more complicated when this turns into a stream of water and this is a comb or a balloon or something. But you get the basic idea. And so yeah, this is an attractive force. The sphere is going to be drawn towards the charge.